Welcome to ALD Stories, a series chronicling the personal journeys of the people behind atomic layer deposition, untold stories of the technology, and deep dives into the history, development, and future of ALD. I'm your host, Tyler Myers, bringing you this podcast from Benek, the home of ALD. ALD Stories is happy to welcome again Jonas Sundqvist to the show for an unprecedented third time. This time, Jonas is here to talk to us about his company AlixLabs and their groundbreaking new technology, ALD pitch splitting, or as they abbreviate it, APS. Now, this recently patented workflow is based on an atomic layer etching process which exploits a newly discovered topographical selectivity, where surfaces perpendicular to incoming plasma etch faster than those at angles. With APS, their team found they could potentially pattern substrates without the use of multiple lithography steps, as is done with current multi-patterning approaches like self-aligned double patterning. After demonstrating a 20 nanometer pitch split on silicon, AlixLabs believes with the APS technology, they can offer semiconductor manufacturers working at leading-edge nodes with a simpler, more cost-effective, and more precise method of creating features with nanometer spacings. Now, Jonas has a lot of great insights here into how APS works, why it's such a unique process, and how it could be a disruptor in the semiconductor manufacturing industry. So I won't try to explain it all now. Take a listen here at the master and talk about his work. So without further ado, please grab your tea or coffee and enjoy episode 20 with Jonas Sundqvist of AlixLabs. Okay, cool. Well, I would say we can do a typical intro, but you are pretty much well-versed in being on this podcast now, Jonas. So Jonas Sundqvist, welcome you again to ALD Stories for your third appearance. If Rika is listening now, she knows what she has to do. She has to come on. Now we have to keep tally of the two of you. So yes, welcome again, Jonas. It's really good to have you.
Thank you so much. It's great to be here with you again, Tyler.
Yeah, I will have to point out from the last time you were on, maybe I'll have to run the clip.
Same here. So it's great to be here again. And I think this is my last appearance.
You did say you would never come on the podcast again, or you said that you probably wouldn't do it a third time. So that will... It looks like maybe we will lost a little bit of foresight.
Yes.
Well, good. So you're joining me today to talk about something a little bit different. We're going to talk about your company, actually, AlixLabs. And for those who are familiar with the ALD Stories podcast, this is mostly about ALD, but this topic is going to be more focused on ALE, which is our first time that we're talking about etching, really, instead of deposition. So this will be really interesting for us. But first, Jonas, maybe you can give us a quick synopsis of what AlixLabs does. You know the technology best, so I won't do my worst to it now. So please tell us a little bit about AlixLab, what you guys are doing, and then we can get right into the really cool technology you guys are working on.
Yeah, so AlixLabs is a spin-off from Lund University in South Sweden. So it's one of the big universities in Scandinavia with a proud history and everything. So, but since I studied at Uppsala University, I will not go into that history. It's a sensitive topic. So I'm only joking. But it was back in 2015. We got tasked with developing a new atomic layer etch process to trim down the diameter of nanowires. So Lund University has a long track record of growing nanowires, 3-5 materials for, nanoelectronic applications, sensors, photovoltaics, biomedical applications, and so on. It's, elementary research and also industrial applications. And in the past, there has been a number of spin-off companies in this area from Lund University. So, but at that point, 2015, the industry, the leading semiconductor companies like Taiwan Semiconductor and Intel, they still had this topic of doing 3-5 materials for future logic chips. And the wires had become a bit large. They were like in the diameter of, let's say, 100 down to 60 nanometer about, as grown. And if you know the transistor evolution, you had, the first iPhone came with 40 nanometer planar transistors, and then it went on to FinFETs, and now we're down at, 3 nanometer, 2 nanometer gate all around nanowire type transistors. So this 60 nanometer was like too big to be also from a R&D point of view. So we were supposed to do an ALE process to trim this down layer by layer to try to reach, sort of 20 nanometer physical distance or go for 10 nanometer even below. So we set up this atomic layer etch process on an old Oxford Instrument Plasma Lab 100 ICP standard reactive ion etching reactor. We looked in literature. It's pretty obvious that if you want to etch this type of material, you should go for argon plasma and chlorine, so Cl2 gas. And then you're supposed to etch cycle by cycle. So we set up like a planar process fairly quickly, like on silicon, to etch silicon. We tested it also on other materials. And then we moved right on to the wires. And we started off, it was just random. We had different types you could pick. And we found, here's a box with gallium phosphide nanowire that Dmitry Soyatin, our CTO, had grown in another project. So we put those in the reactor, and to our surprise, they didn't etch as we wanted it to do. We were really focusing our brain power to try to get physics and chemistry to work for us, like in the plasma, but it didn't work. So they came out splitted. Like if you think about the log canoes, like in the Stone Age, where you chop out the center of the thing. There are some pictures here, so you see they looked like this. You had original nanowire about 60 nanometer across, and then we etched out the center. So we basically split it in 2 nanowires. And then we tried it on silicon nanowires, sort of 100 nanometer diameter. We also splitted it, so it seemed, we thought this was like a crystalline effect because these are hexagonal, whereas these are round, but we could also split round nanowires. And we manipulated some samples next to each other, so we could do like a pitch split. So here's 2 wires with the 2 times bigger pitch, and we etch both of them and we have half the pitch. So that's when we realized that we have a new pitch splitting technology, and we decided to file patents on this.
Yeah, this is pretty incredible stuff here. I think anybody who's familiar with etching would probably presume, as you might have, that you were just going to shrink the wire isotropically or so, right? Yeah, just and make it a thinner wire. So having this be the outcome, I'm sure, was pretty surprising for you.
Yeah, so the last thing we did was to actually do the transfer into silicon. So here is bulk silicon. So we did a split and transferred into silicon and created 2 fins in silicon. And this is, if you look at FinFETs and stuff like that. Yeah. So this is the technology we are further developing on wafer level. And that's the way we want to go to make this a 300 millimeter silicon wafer process. So
that's great. That's fantastic. Yeah, I think there's a lot to unpack here about this technology that you guys have. I mean, first off, imagine this is really quite the disruptive technology, and we'll get to that in a second. But just on a pure interesting technical basis, you essentially discovered that you have some type of topographical selective etching happening with these, right? So rather than this isotropic etching, you were seeing the etching only happening on the incline or on the perpendicular surfaces and not on the inclined surfaces, right?
Yeah. Yeah, so I mean, ALD people, they feel comfortable talking about the ALD window. And when you have selective ALD, like you can have selective ALD on metal, but not on oxide. It's, something that most people discover when they start with ALD independently of each other, that this is the case for certain processes. And then you usually talk about, okay, I open the ALD window on metal, but it's closed on oxide. And it's basically the same thing here. We open the window on the horizontal surface, but we keep it closed on the inclined surfaces. So there's just no ALE going on the inclined surfaces, only on horizontal surfaces. And the reason we can do this is because we're working in a plasma mode, so we have a directional ion beam from the top, which is perpendicular to the horizontal surface, the structure. So we talk about that we have topology, so we have a topological mask rather, and it can be the same material as you want to etch. So you don't need to have an additional hard mask on top. You can just shape whatever you want to etch that you have an ALE process for, so it seems to be generic. And then you tune the process parameters that you only open the window on horizontal. And then you will etch layer by layer down there, whereas the inclined surface remains standing. And that's what you see with the split of these wires and silicon. So here we have done this. We have opened only for the directional etch of. So the surface here you see has this surface was up here originally. And it's now, there is no masking or splitting going, it's just generic ALE planar, and it's just etched all the way down. And here we have initiated the split and then gone down into the silicon. So this, so that's, where we have filed and got a lot of approved IP around how to do this, and we continue this R&D to, and I can describe the process in maybe a pedagogical way, or at least I try to, because you can imagine that we have talked to the real experts, not like anyone on the street, like real experts at semiconductor manufacturing companies, the big guys, and they don't be ashamed, they have problem understanding this. So this is a 10-minute preaching that each meeting with them starts with that we explain over and over again how this is done, because it's not intuitive. Because Dimitri would tell you that what you would expect is that you start to round off the corners and etch preferentially at the corners and have some sort of sputtering effect, erosion, and this is exactly the opposite. And that's why it's so hard for an etch expert to see that this is possible. So I had the advantage of being an ALD guy and had no clue about etch. So I could just accept what I was seeing, because I didn't know about the corner effect or whatever they call it. So to me, it was, what's the corner effect? Who cares? Etching, it's like selective ALD, Selective ALD also exists that you can, bottom-up growth, sideway growth, top growth, material selectivity. It was like natural to me, but that it should also occur in ALE. But yeah, we did several deeper dives into filed IP, and there's nothing like this filed.
Yeah, I think from my side too, also as a deposition expert, I think it didn't seem too far-fetched that you might have selectivity in that kind of way, and just, there must be some reason. Yeah, I had no preconceived notion as to why that couldn't be the case to begin with. But yeah, so this is very cool, what you call now atomic pitch splitting, APS, and this technology is very, very much a departure from how this kind of patterning and whatnot is done in traditional semiconductor processing. I mean, multiple patterning has been proved upon many, many, many times, but this is a very different way to do it, removing a lot of steps. So could you speak on what the implications are if you were using this type of process versus how multiple patterning is done now?
Yeah, sure. So, I worked on double patterning, the first version, when I was in the semiconductor industry at Qimonda. So I did this with ALD, so because it was a strategical project for Qimonda while waiting for EUV lithography, it was clear that we needed an alternative. And self-aligned double patterning, it was invented by MIT, like early 80s sometime. And the IP foreground, the prior art was free for anyone to use, was the situation. So that what happened was that all companies developed their version of double patterning and filed IP of that. And so basically you have one ALD process step and at least 3 different reactive ion etch chambers you have to pass the wafer through. So you see, it's like 4 process chambers, each costing, $1 to $2 million per chamber, times 4, and clustered on advanced tools from leading edge suppliers, tier 1, the big guys, ASM, Applied, Lam, Tokyo Electron, and these guys. And that had to work in a flow with intercepted metrology to keep, policing the process, how it's going on. In the end, you have a whole very complex process. And it's all lithography spec on it, since you define, the size of, in DRAM case, the shallow trench isolation for the transistors or the capacitor widths, and in logic it's even worse. You define the channel length of the transistor with this type of process. So if I add an ALD cycle in the liner, I can change the length of the gate coming out and the speed of the transistor. So this has to work perfectly. You don't want to have processors in the center. Oh, they are really fast, let's sell them to Apple. And this one on the edge, they are a bit slower. They can go to some microwave application or something. That's not how it works. Apple will want to buy the whole wafer, and all transistor has to have the same length. And this is the complexity of this process, to keep this spec through deposition, etch, without losing it. And they have to work together. And by putting this all into one process chamber, we take away that complexity, that drift. So we simplify the problem that we have a pre-measurement. We decide how many ALD cycles we initiate in the split and how much we split. And then we do the transfer split to the next layer in one process chamber. And it's the same, basically the same process. Replacing one depth chamber and 3 edge chamber into one. So, if you're an equipment vendor in this field and you cover the whole base, like Tokyo Electron, Applied, and Lam, they can sell the deposition chamber or the etch chambers and put them on a cluster. And then these crazy guys from Sweden come and we just need one chamber. And this is a repetitive process. You can do quad patternings in 2 chambers, and it comes for 10 to 20 mask layers. So it times 10 investment space that just shrinks. So obviously, if we succeed, this will be very disruptive in the business segment, which is a big business segment for ALD and etch. So that we are aware of this. And so our problem is to sell such a wonderful technology you can't do with this type of results. So we need to have this on 300mm wafers. And that's the biggest barrier we have to succeed now. So physical, chemical barriers we have, punched through. We have physical evidence that we can do this in silicon. But we don't have that on 300mm wafers, which has been patented by, immersion lithography or even better EUV lithography. We don't have that. And so this is, for our next 2 years, that's our single purpose of the company. We don't have any other purpose than to make those wafers.
Yeah, okay. So you have to go from doing it one time in one place to doing it, orders of magnitude more times across an entire 12-inch wafer.
Yeah.
Yeah, I imagine that's quite a big undertaking for the next couple of years.
Yeah, so that's our plan, and that's what we're going to do simply.
Great. So you're saying basically you have these cluster tools that have multiple steps. You need to break vacuum, move to another tool, and you could do all of this essentially in one chamber, just etch, basically, until you get to what you need to. So then theoretically, what's the limit that you see, or is there a limit to how small you can go, how tiny the pitch split can be using APS?
Yeah, so all I can tell you that we have, you see here we have 10 nanometer. That type of feature we have initiated a second split on. So we think that we already have, lab proof that we can go down to 2 to 3 nanometer. So we have an internal joke and that's if you have 3 atoms, we can remove the one in the middle. So I would say that that's the limitation. So
basically as small as you can go.
yes, another joke we have is whatever they can do, we can go one step further. So
Okay.
like they have now UV lithography. So the Intel, Samsung, Taiwan Semiconductor, they have this, and they have, for their latest logic, they have maybe 20 mask layers with UV lithography planned, hooked up, and some of them they have to do double patterning on, and this is expensive, and we think that we can also be helpful there. That okay, do EUV like you're supposed to do, but let us stay at one exposure, and then do a split with this type of technology. So it's not. Some people misunderstand us that we are competing with EUV lithography, but we are really complementary to lithography, and we compete with double patterning, quadruple patterning, these type of implementations. So this you have for NAND flash, when it was still two-dimensional, they were early taking on double patterning. DRAM has it, logic has it since 20 nanometers. There's a lot of fabs out there that run double patterning, like 20 nanometer fabs, 14 nanometer fabs. They have double patterning, and they are still building those types of fabs. So we think that we have besides this secondary, this leading edge market, which of 3 nanometer, 2 nanometer, 18 angstrom, and so on. We think that we have existing market of fabs that came online the last decade that could try to intercept and swap out some of the double patterning steps with this type of technology once we have a mature technology to roll out. And logic fabs, they exist for very long. It's like nuclear power plants. You build one, and the only reason to remove it is political reasons. It's a 28 nanometer fab today will be a cash cow for so long, and they continue to tweak the cost performance of such fabs. Taiwan Semiconductor, China, SMIC are still building huge capacity of 28 nanometer. So it's not like a dead field. So we think that you could go in and tweak those and let them go down to 14 nanometer by introducing the more cheaper way to do double patterning. So I think we have a chance both in leading edge, but also in existing fab infrastructure. And I mean, we are in Europe, and you can look at the European landscape. You have here where I'm in Dresden, it's GlobalFoundries lead fab. They do 28 nanometer and 20 nanometer. I think that they have double patterning at 20 nanometer. So we could come in there and at some point in time and have an attractive offering for them to improve that module. So that's what we think. And the other point is the complexity. We bring down the complexity, which helps doing yield, and you can increase the yield if you have lower complexity. That's sort of a general no factory physics. That's just how it works. And then the environmental impacts, we are starting such studies, since if you remove stuff from the fab, you sort of automatically work more sustainable, because everything in a fab that you do is not sustainable. So we are starting to calculate what the upside is from that perspective also. So yeah, a lot of interesting upsides we find.
Yeah, absolutely. I think, again, a lot that we could unpack in those advantages here. I think one, just to start from the lithography point of view. So if you are limiting now to one EUV lithography exposure at the beginning instead of multiple and a litho etch type of process, like how much cost savings do you expect that you could see if you were using the APS and removing some of those litho steps?
Yeah, so we did sort of a meta study. So we took an existing study, which was sort of independent. You don't want to pick one from ASML or one from Tokyo Electron, you have to find someone who doesn't have the commercial interest in this process. So we found one from TechSet. Ed Korsinski, he presented it at SPI 2019 or so. So he did a apples to apples comparison of all ways to get down to 22 nanometer physical pitch. So not technology, but physical pitch. And I got access to the data, and I just started to remove process steps that we don't need. And then you could see in Excel how like the cost projection just dived. Let's remove this etching. So it's really overall, we think in this specific comparison, you compared cost per wafer pass through this whole process module. And typically these processes at full production was in the range of $35 to almost $40 per wafer pass through the process for all. They spit out 100,000 wafers per month. So this times 100,000 to start with. So $35 times 100,000, that's the cost of one litho layer through double patterning per month. And we were able to get it down to about 35 to 45%, so less than 50% of these versions we benchmarked. And we benchmarked doing quadruple patterning and EUV, double patterning and quadruple patterning, directed self-assembly. Everything that was on the market 2019 was in that model, like proven on 300 millimeter. And we put in our lab data into that model, and we immediately see cut the cost in half. And now we are collecting, we are moving into 300 millimeter. We will learn more about the cost of ownership of this process. And at some point we will have direct comparison with double patterning. Then we will move on to a direct comparison with quadruple patterning. And then if we can do that, we have a very attractive proposal, I would say.
Yeah, it's really incredible. And just as you were mentioning, the leading edge nodes, and then you have the ones that are a little bit further behind, but that they're not going anywhere. And I'm sure there will be more and more fabs that are initially repurposed from their higher nodes down to lower nodes as well. So having some kind of technology like this really cuts that barrier to entry to get down to some of these nodes as well. You couldn't get all the chambers and tools that you needed before. You could do it all in one. So you really could be enabling a lot more fabs to go down to more advanced nodes than they could have been before.
Yeah. And I mean, you're an ALD guy, and obviously anything you can do with ALD is quality-wise so much better than CVD. And we argue in the same way. We do atomic layer etching. It's damage-free, low damage. You have lower surface roughness at the etch front than compared to standard reactive ion etching. So we have those generic, ALD, ALE advantages that, surface area insensitivity. So if the mask is designed differently for different customers in a foundry, we will have the same splitting results, because it doesn't matter how much surface loading we have, because it's a self saturative process, just like in ALD. That's all. I mean, that was the reason why ALD was used for double patterning as the liner and not CVD, was because the CVD was design sensitive, because you had to adapt the CVD process all the time for different designs, whereas the plasma ALD process for the liner just doesn't care too much about if the design goes to Qualcomm, Broadcom, or some other company. It's just perfect liner all the time.
So then you said you're dedicated the next 2 years to transferring the technology to a 300 millimeter wafer. So then presumably once that task is overcome, so then you're going to be looking at, I presume, traditional memory logic applications for this technology, I would say, right?
Yeah. So our plan is to license this technology to the end users, so the fabs in our case. So we are segmented the market into logic wafer fabs and foundries, and looking first at the advanced ones, or the leading founders. So it's Intel, Samsung, Taiwan Semiconductor, and that gang. And then, of course, the memory makers. So here we have the DRAM, and we see the need in DRAM because in DRAM you have, since quite a time, quadruple patterning, and double patterning is standard since long time. So they are really the experts on this. And they are a bit more cost sensitive when it comes to, they would not like to have 20 EUV mask layers, because then none of us would afford buying DRAM anymore. Or maybe that's their secret dream. They want that, but that market is not available. So they need to look at costs much more than the logic guys. And maybe they can have a couple of EUV masks like Samsung and Hynix has, but recently, like Micron announced that they are on their new latest node of DRAM 1 beta, what they have ramped in their Japanese fab in Hiroshima. And that has a proprietary multi-patterning scheme. So that's obviously, wow, yeah, that's our guys, you know. That's what we want to hear more of that, like because then we can, we have our proprietary multi-patterning scheme, and it's much cheaper than your proprietary multi-patterning scheme. So that's exactly, timing is pretty good for us now. This is exactly what the industry needs, because the cost per wafer coming out of TSMC is, going upwards. When we had iPhone 1 with 40 nanometer technology, a TSMC wafer, when it popped out in the back end from a TSMC fab, cost $2,500. Now 3 nanometer, that wafer costs $20,000. It's, almost a factor of 10 going from 40 nanometer iPhone 1, and now we have iPhone 14, right? They're gonna have those wafers. And the phone you bought, the first iPhone everybody bought, had a different price than the iPhone you have now. It's more like an investment. And it's not only this type of technology, leading edge 3 nanometer. It's not only in the application processors. You have all these 5G chips. They are also foundry chips, also use advanced technology. So in the phone, you have so much more silicon these days. I think if you look at one of these teardowns, it's something like 25 different chips. So backside, I have 5 cameras, 1, 2, 3, 4, 5 chips. There's LED lamps. It's also sort of a chip. Then if you would open in, you have the DRAM. It's all advanced patterning. 3D NAND for the solid state hard drive. It's also advanced patterning in there. So our goal is to be in those phones for one mask layer. If we reach that, we can be very happy, I think.
That's great. So then, just from a logistical point of view, where do you see AlixLab growing from now? Are you looking to build the team soon? Are you happy with your core right now?
Yeah, we are really happy with the core. So we need to build more outside the core. So we have a strong foundation, 5 R&D people running the development. So me, Dimitri, Reza, Amin, and Joanna, full-time employees. Everybody is, nano people with PhD or soon to get PhD. And we're building up, we have a board based on industry people from semiconductor industry, telecom, legal, IP. So that's a good board to move ahead with. And we are adding advisory board, and then we have consultants for financing and legal and IT and so. But we need more hardware people. We will need more process people, because we operate more and more tools. So at the moment, we're operating 3 ALE chambers, our own, and 2 at Lund University. And we're also starting activities in Germany with Fraunhofer 300 millimeters. So we will need more process people, so dedicated to each. Usually what you have in industry is you have, process owner, and it's usually one tool, one engineer. And as you progress, you get more chambers. So the senior guys, they can have several chambers, but you step in and learn everything with one chamber. So this is sort of how we're doing it. So we will once we understand our own chambers, we will have to understand other people's chamber, customer chambers, in order to do effective process transfer from our to the customer. And that's going to be a whole new learning for the whole team, I think. And we will have to take on more, experienced fab people who has been running around in the fabs with the wafers and running design of experiments on expensive wafers. That's also cost will go up when we start to do this, so we will have to take on board more money. So they are running now new investment round in the company that's going to close first quarter next year. So any rich guys out there, you're welcome to AlixLabs. Give us a call.
Right, that's exactly what you do. We're recruiting with the podcast now.
Yeah.
So then, you probably don't have an answer or don't want to say an answer, but when can we expect to see AlixLabs inside our iPhones?
Yeah, so early on we were hoping for iPhone 16. So, that's Christmas. Now we have 14 for this Christmas. So let's say Christmas 2026. But then if you calculate backwards, those wafers needs to start in Taiwan summer 2026, which is a bit tight to make, because the Christmas wafer starts already in summer, because it takes some time for them to go through the fab, and then they need to go to, Foxconn, they put it in the iPhone and backend and all this, and then they ship it to the distribution centers. So it has to come to Ireland, and then it's distributed all across Europe. So we don't think we're going to make that one. So we have moved ahead and maybe iPhone 17.
All right. Fantastic. So does that mean 2027, all AlixLab employees get a iPhone 17 as a Christmas present?
Yeah, that. And for the left hand, they will get the Samsung Galaxy.
All right. Well, fantastic. Jonas, this was really fun. You guys have such a cool technology here at AlixLab, and one that's, like I said before, is quite a departure in innovation that we've seen in multi-patterning for quite some time now. In many decades, we've been kind of hammering away with deposition and lithography and kind of trying to extend that as far, and nobody has quite come through with an innovation in etch yet. So I say congratulations to you and Dimitri and all the rest of AlixLabs right now for your patents and the funding and all of the progress that you've made so far. I'm really excited to see where you guys go in the next couple of years.
Yeah, thank you, Taylor. So it's nice to be the third time on your show, and let's see if we come up with something big like 2026. So let's see how far we are from the iPhone and the Samsung Galaxy. Maybe it's time for a fourth time.
It might have to be. That sounds great. Well, thanks again, Jonas, for coming on. This was a blast, and I'm looking forward to everything to come. And hopefully we'll be seeing you in Bellevue then in July next year.
Yes, sure. Have a good day.
Okay, thanks, Jonas. You too. Take care.
Take care. Bye-bye.
Bye. Thanks for listening to ALD Stories with Benek. To stay updated on new episodes each month, please follow us on Spotify, Apple Podcasts, or Google Podcasts. We hope you enjoyed the show. I hope to see you again in the next one.